Hope y'all had a good weekend. What we are going to do today is start into the last unit of the class. This is going to involve two kind of broad categories, namely the Enolate Chemistry that we'll start with first, and then we'll end the class with a section on biochemistry, focusing mainly on carbohydrates and protein. So, with this last unit, I'm going to just kind of give you some broad outlines of it, and then we'll jump into it. There's good news and there's bad news. So the good news, well, let me give you the bad news first. The bad news is the Enolate chapter tends to be challenging at first for most people. It's not really that the chemistry is all that bad, it's just that you're going to learn probably in and around 10 reactions, specific reactions, and the problem with them, what I've experienced in the past, is that they all kind of look alike, and so they can be kind of difficult to distinguish one from the other when you're first learning them. So it just takes practice with them. And so I'm going to introduce all of these reactions in terms of functional group transformation. And that's the way I would encourage you to learn them. If you can look at them and say, okay, well, I'm starting with an aldehyde or a ketone and I'm ending up with this new functional group, if you can kind of learn them that way, it makes them a lot easier to distinguish one from the other. Okay, but if you're just looking at, okay, I'm starting with a bunch of carbonyl compounds and I'm getting this product that has some carbonyls in it, they can all kind of blend together. They can all look very similar to each other. But learn them through functional group transformation, and I think you'll have a lot easier time with distinguishing one of them from the others. Okay. Now that said, this chemistry, the Enolate chemistry, is really the kind of the pinnacle of synthesis for this class. All of these reactions are going to be carbon-carbon bond forming reactions. And as we've talked about, that is kind of the bread and butter of organic synthesis. If you're trying to build organic molecules, by definition, you have to be able to make carbon-carbon bonds. And all of these reactions will allow you to do that. So it would be hard to overstate how important this chemistry has been, especially throughout the 20th century. It's basically the way organic synthesis was done throughout the entire 20th century. So it's very, very important, both from a synthetic sense and also a historical sense. So the good news, though, is once we get through the enolates, which we'll probably be focused on for most of this week, the good news is that when we reach the biochem, after all the torture you've been put through for the last 2 semesters or semesters and 3 quarters, whatever it's been, I think you'll find the biochem pretty easy. So it's kind of nice, you got to struggle a little bit through the enolates, but then we'll finish off with the biochem, which will be, in a relative sense, pretty easy, and we kind of coast to the finish line. Okay. So, before we get started, does anybody have questions on the last couple of weeks that we have together? Yeah.
Will you post the Unit 4 so that we can print the slides off?
Oh, is it not posted yet? Oh, my bad. Sorry about that. Yes, I will do that as soon as we finish up here. And actually, if you would like me, I can do it right now. Okay, then I will do it as soon as we leave here, and you should have access to everything by the end of today's lecture. Okay. Yeah, sorry about that. I thought I had done that already. Okay, so let's go ahead and get started then. What we're gonna, let me start this recording just a second. Okay, so this is going to get us into the chemistry of enols and enolates. So I will begin talking about enols, but we're going to spend just a very, very small amount of time discussing enols because they're not really all that useful. The enolates are by far the majority and the most useful part of this chapter. And whenever I talk about an enol versus an enolate, all I'm talking about is a difference in the protonation state. So for instance, an enol is going to look something like this. It's a neutral intermediate versus the enolate is the ionized form. And as I said, we'll talk a little bit at the beginning about enols, but we're going to focus this chapter primarily on the enolate. Okay. So how do these form? Well, they're pretty much always there. You have these ever present when you have carbonyl compounds. So you probably learned in Chem 420 that I'll just use a ketone, but you can use any carbonyl compound really. But anytime you have a carbonyl compound, in this case a ketone, it is always in equilibrium with a very, very tiny amount of the enol, right? This is what we refer to as keto-enol tautomerism. You've probably heard of that before. But the enolic form of this is present in a very, very small amount. So probably around 0.01% of all of the molecules in a sample of a ketone are going to be present in this enolic form. And so if you're thinking about trying to do a reaction that relies on this enolic form, well, you're going to have to do something to get a little bit more than 0.01% of your molecules in a reactive state. And so it turns out that it's fairly easy to get more of this enolic form. You can do this under acidic or basic conditions. And so what I'm going to do, I think first, is illustrate the fairly simple mechanisms of enol formation. Okay? So like I said, you can do this under acidic or basic conditions, and the mechanisms are very, very similar. So let's go ahead and start with how acid and base actually initiate this enol formation. So under acidic conditions, you have a ketone or aldehyde, whatever the carbonyl is. You can imagine if you add acid, the first step is always the same, right? We've seen this pretty much all semester long. If you add acid to a carbonyl compound, what's going to happen is the carbonyl goes out and protonates. And at this stage, what's going to happen is the water is going to grab the alpha proton. That does two things. It's going to generate the enol, and it also regenerates the acid catalyst. All right. So you'll note in this mechanism, we simply did a two-step process. It was a protonation, followed by a deprotonation. All right. So then in base, what we're going to see is the exact reverse of this process. Okay, so under base catalyzed enol formation, we're going to take the ketone, add hydroxide, and instead of doing a protonation, deprotonation, we're going to flip that and we're going to do deprotonation followed by protonation. Right? So the base would come in, it's going to grab the alpha proton, that generates the enolate, which then can grab a proton from the water. And that regenerates the base catalyst. So under the base catalyzed mechanism, we did a deprotonation followed by a protonation. All right. So fairly simple mechanisms, but both of those conditions will give you a more useful amount of the enolic form, at least enough to where we can actually do chemistry with. Now, I think it's important at this point to look a little bit more specifically at this first step of the mechanism, the hydroxide going to grab the proton from the alpha carbon. I mean, if you think about that, what we're doing here is we are deprotonating a hydrocarbon. And that should seem a little bit unusual. Let me show you something just in a way of an analogy. So if we were going to try to deprotonate these protons down here, do you think that would be an easy task? Could we just throw in hydroxide here and make the C- species of this alkene?
I think it'd be easier if it was just like cyclohexane.
Yeah, you're right. Those allylic protons would be more acidic than if it was just cyclohexane. But if you put hydroxide here, would you be able to deprotonate that? It turns out the pKa here, it's so high, it's hard to accurately measure. But somewhere on order of 45. You are never deprotonating that with hydroxide, is the bottom line. And yet, here we are with this enolate type situation where you're using hydroxide to deprotonate a CH. It turns out that the pKa, so what I'm trying to point out to you is that that alpha position is unique in carbonyl compounds. It is much, much more acidic than a regular CH position. And just to give you some numbers here, the alpha position
When you say alpha, what do you mean alpha 2?
Oh, it's the alpha position is just the position just adjacent to the carbonyl.
Okay.
So those alpha protons, they have a pKa of roughly 20. That is a huge difference in acidity for seemingly kind of similar protons. Right? Anybody know or think of a reason why there'd be such a huge difference in the acidity between these alpha protons and kind of allylic protons?
Is it because of the electronegativity of the oxygen wanting to keep the electron?
Yep. Because imagine what happens if you were to add base and deprotonate. You would get something that looked like that, which, yes, the carbonyl right next door does have some electron withdrawing effect, which would help to stabilize the negative charge, but we can do one even better. There's a second resonance form where we can actually push the electron density into the carbonyl. So basically, having the carbonyl present allows for the delocalization of that negative charge. Right? If and as you know, we've talked about this from the very beginning of the semester. To the extent that you can delocalize electrons, you're going to be all the better for it, right? The electrons don't like being right next door to one another. They like to be spread out from one another. And so by having the carbonyl present, it allows the delocalization of that negative charge. So that's why it becomes so much easier to deprotonate these alpha protons compared to other regular CHs. And that's going to be what we're going to do for this, pretty much this entire chapter. We're just going to be using that alpha position to go out and attack things, to go out and act as nucleophile. Oh, by the way, it's a totally random topic, but it just reminded me of something that I saw on exams more than I think I should. Whenever you're drawing a mechanism, just for the record, if you're talking about trying to protonate a carbonyl, for instance, which we very often are in this class, when you're drawing your arrows, I saw a lot of people do this. What's the problem with that?
It's not the direction that electrons went.
Yeah, your arrow's in the wrong direction. Right, remember what arrows indicate in mechanism. In mechanism, arrows indicate the flow of electrons. Well, you cannot have a proton with an arrow to an oxygen because a proton has no electrons. Right, arrows indicate the direction of electron flow. If you have no electrons, obviously they cannot be flowing into something else. Right, so this is absolutely incorrect. The way we would draw that would be the nucleophile attacking the electrophile, not vice versa. Okay? So, sorry to digress on that, but in any case, so let's go ahead and look first at some reactions that we can do with these enols. So like I said, we're not going to spend a lot of time looking at reactions of enols, just probably a couple. But we'll look at those first, and then we'll transition into the much more useful enolate chemistry. All right? So one of the things that we can do with these is we can halogenate. So what we can do, I'm going to kind of show you a generalized reaction, and then we'll look at the mechanism together. If you take an aldehyde or a ketone, we can take a molecular halogen, and we can add that to the alpha position. Now, a couple things about this. In terms of what your halogen can be, it can be chlorine, it can be bromine, or it can be iodine. So like most reactions that we've seen involving halogens, we're not going to do it with fluorine. It's just too reactive and generally causes fires and explosions. So chlorine, bromine, iodine. And then the other thing about this is that you're not going to be able to do this with all carbonyl compounds. All right, you're only going to be able to do this for aldehydes and ketones. So the problem you have with, say if you're going to try to do this with a carboxylic acid, the problem with trying to do this with a carboxylic acid, well actually let me go through the mechanism first and then I'll show you why this is only going to be good for aldehydes and ketones. So if you're going to do this reaction, you can do it in acid or base. Remember, can generate the enol under acidic or basic conditions, and so you can do this reaction in acidic or basic conditions. So to do this under acidic conditions, the way you typically do it is you use acetic acid. And the acetic acid is going to do two things. It serves both as the solvent and as the acid catalyst for enolization. So under these conditions, you will form the enol, which I don't think we really need to go through again because we just saw how that was done. But you would make the enol. And then the enol is going to push the electron density out of the alpha position like this. Electrons come down from the oxygen and get kicked out of the alpha position. And then all you have to do is a minus H plus step. Reform the acid catalyst, and you end up making the alpha halocarbonyl. Now in base, there is a difference. So you kind of go through the same process. You enolize. Something like that, and that's going to give you again the alpha halo carbonyl. The problem with doing it in base, however, is you have another alpha proton. And in fact, this alpha proton here is even more acidic than the alpha protons of the starting material. Remember, you have an electronegative atom attached. And as a result, that alpha proton is more acidic than the starting material. And so what ends up happening when you do this in base is it's hard to control. You tend to start getting multiple halogens added. So because of that, if you're going to try to just make an alpha halocarbonyl, you never do it in base. So maybe we'll write not synthetically useful. Because again, it's difficult to control. You get multiple halogens adding. So if you want to try to do this, you're always going to use the acidic conditions. All right. So why is it that we can't do this with something like carboxylic acid, for instance? The problem has to do with the enolization. So in order to do the halogenation, you have to be able to enolize. So think about what that means. If you've got a carboxylic acid, under some conditions, acidic or basic, we need to be able to do this. It turns out that's very difficult to do. In fact, maybe it would be better if we through the equilibrium like that. The reason that's so difficult to do is because the carboxylic acid already has a lone pair atom attached. Right? The aldehyde and ketone don't have that lone pair containing atom attached to the carbonyl. Right? The problem here is that because you have a lone pair atom attached here, you have electron density being kind of pushed in from the right in its normal state. And so if you have electron density being pushed in from this lone pair atom, it's going to be increasingly difficult to also push electron density in from the left. And as a result, the enolization just doesn't work well here with these carboxylic acids. The same thing would be true for an amide, really any kind of a heteroatom carbonyl functional group. Right? The enolization just happens to such a small extent. And thus the reactions don't work well at all. So that's why I say if you're going to try to do this alpha halogenation, you're going to want to stick to aldehydes and ketones. So what's the point? Why would it be useful? Why would you want to make an alpha halo carbonyl compound? It turns out that they undergo elimination readily. So it's a very nice way of, through the use of just very weak bases often, something like pyridine and heat would work. You can cause their elimination, and it gets you access into these alpha-beta unsaturated carbonyl compounds, which, as you'll see in the future, are quite useful. Now, if your goal was to make an alpha halo carbonyl compound, you could have done that without knowing this chemistry. All right, so if I wanted to make an alpha halo carbonyl, we could have done it I'm gonna maybe start with cyclohexane, do a photohalogenation, eliminate, do a halohydrin, and then oxidize. So I mean, you could have done this before. This is just a much more direct way of doing it. Okay. All right, any questions on the halogenation reaction?
For the acid catalyst and the base catalyst, how did you first find that little bond?
Of the enol?
Yeah.
Let me go back to the mechanism here. Oh, there we go. So, with the acid catalyzed form, you protonate first, you make this good electrophile, and then water can come in and grab the alpha proton and push its electrons in to the carbonyl. Under the basic conditions, the base, because the alpha position is relatively acidic, the hydroxide can come in and grab that alpha proton directly, and electrons go into the carbonyl like that. Okay, so doing a direct halogenation, as I mentioned, is only going to be useful for aldehydes and ketones. That's not to say you can't make alpha halocarboxylic acids. If you want to, you can. You just have to use a slightly different approach. And this is a well-known reaction. It is what's called the Helvol-Zielinski reaction. most of the time, people just abbreviate this as HBZ. But what Helvoll or Zielinski does is it takes a carboxylic acid and it treats it with a handful of things, phosphorus tribromide, the molecular halogen, and then water. And what that does is what I told you you can't do directly. It simply takes the carboxylic acid and puts the halogen in the alpha position of it. Okay. So the reason why this works, whereas the direct halogenation didn't, will become, I think, apparent as we look at the mechanism of this. So what do you think is going to happen first? What happens if we take a carboxylic acid, or really anything containing an OH group, and we give it PBr3? Yeah, exactly. We're just going to put, instead of an OH, we'll substitute the Br. So nothing new there. So the first step is the conversion of the carboxylic acid into the acid bromide. Now, in the course of this reaction, you generate some HBr. And that HBr that's generated through this reaction is enough to cause the enolization of the acid bromide. So I think I'll put the HBr in parentheses because it's not like you're directly adding HBr to the reaction. It's just generated as you form the acid bromide. Right? So that HBr is enough to cause the enolization like that. Well, why is it that we can enolize the acid bromide, but we couldn't enolize the carboxylic acid? Well, you're right, the Br and the oxygen are not the same, that's the crux. The problem is, remember, the reason why we couldn't enolize the carboxylic acid is because you had electron density being pushed into the carbonyl from the oxygen. Now, theoretically, that could also happen from the bromine. I mean, you've got plenty of lone pairs there. But in order to push electron density from the bromine, remember what we're having to do, we would need to form kind of a double bond between the carbon and the bromine. To push electron density into the carbonyl from bromine, you have to make a pi bond between the carbon and the bromine. Well, this goes back to something we've seen on a number of occasions. Bromine is not the same size as carbon. Its orbitals are not the same size as the orbitals on carbon. And so this trying to make a pi bond between a bromine p orbital and a carbon p orbital is not going to work. Whereas it's very easy to form a pi bond between a carbon and oxygen because they're essentially the same size. Okay? So the bromine pushing electron density, yeah, Ethan, you're right, it's not as nearly as electronegative, but that would kind of argue the opposite. It's more of a resonance thing. The resonance donation does not work nearly as well with the bromine as it does with the oxygen. So this can enolize pretty well. And as soon as it enolizes, that's when the electrons come down, get kicked out the alpha position. Do a minus H plus step. What do you think the water is doing in this reaction? You know, if you just add PBr3 and bromine, you end up getting to this place right here. What is the water going to do? Yep, the water is just going to come in and hydrolyze the acid bromide and give you back the carboxylic acid. So while it looks as if the Helvoller-Zielinski is a halogenation of carboxylic acid, it's really not. Right? It's actually the halogenation of an acid bromide. All right. Okay, so those are the main two reactions I wanted to talk to you about that use enols. The rest of this chapter, we're going to be looking at enolate chemistry. And, you know, it's nice that we can put halogens on the alpha position, but let's kind of branch out into even more useful chemistry, and that would be thinking about putting things like alkyl groups on the ring, doing carbon-carbon bond forming reactions with this enolate chemistry. So one, you might think that direct alkylation could be used here. What I mean by direct alkylation is if we were to take a aldehyde or a ketone and treat it with hydroxide, we can generate the enolate. And instead of adding a halogen now, what if you used some other kind of electrophile? Like a carbon-based electrophile. You know, something like, I'm just going to use a generic, say RX. This should be able, in theory, to do something like that. And give us a way of functionalizing these alpha positions. That would be a very useful and versatile reaction. It turns out that this direct alkylation really does not work all that well, though. And so I'm going to show you why, and then I'm going to show you a couple ways of doing this better. So the problems of this direct alkylation, one of them has to do with just the base strength. So let's think about this first reaction. The first reaction is the deprotonation of the alpha position. So I'm going to do this, I'm going to write out this ionization expression like we were back in Gen Chem for a second. So the pKa, as I said a minute ago, of the alpha position is approximately 20. So when that deprotonation happens, our product side is going to be the enolate and water. Well, think about what the pKa of water is, and that will tell you the position of this equilibrium. What's the stronger acid? The alpha protons of the ketone or the conjugate water? The water's a stronger acid. It has a lower pKa. So what that means is that water is more likely to do without its proton than the ketone. Meaning, this equilibrium favors the reactants. So, the issue is, you can mix a ketone and hydroxide, but you do not get 100% of the enolate from that. Because the equilibrium favors the reactants, once you let them mix together and come to equilibrium, you're going to end up with a whole bunch of this still in solution. Yeah, you'll make some enolate. You can do some chemistry with it. But at equilibrium, you're going to have a whole lot of this still around. Think about what that means in the context of your reaction. You're trying to do an SN2 chemistry here. So if you mix these two, and at equilibrium you end up with some of that and a whole lot of this still around, and then you throw in your electrophile, well, you would have a situation of two nucleophiles. So yeah, this enolate, the little bit that's formed, could go and attack and give you the substitution product you're trying to get. But you have a whole bunch of hydroxide around also that's going to go in and attack your electrophile. Furthermore, let's say you do make a little bit of this. Well, you still have a bunch of hydroxide around, so the hydroxide now can come in and attack those protons. And this can go and alkylate. So you end up getting, it's really quite a terrible way of doing this reaction. I'll outline, just to kind of enumerate the problems. Number one, the hydroxide can come in and attack your electrophile. Okay. Second one, you can get polyalkylation because the excess hydroxide could come and deprotonate this thing, and that can react again. So polyalkylation is a problem. And then the third thing is, you can't do this with aldehydes. They undergo a side reaction that we'll talk about later. So this is kind of plagued with issues. And just to kind of give you some actual data on this, if you were to try to do this reaction, you end up getting this mixture of products. What you'll notice first is that doesn't even add up to 100%. Because, as I said, a lot of your electrophile is going to get attacked by the base. So that just kind of takes it right out of the equation. But the products that you do get are a lot of different products, and no really good yield of any single one. So again, not the way you want to do this reaction. So most of the issue that we had when trying to do this direct alkylation lied with the choice of the base. Our base wasn't strong enough. So one way of getting around this is by just using a stronger base. And as you'll see, as we go through this chapter, we're going to use this a lot. And it's a new one I don't think you probably know quite yet. A better way of doing this is using a base that's called LDA. And LDA stands for lithium diisopropyl amide. So it looks like this. So you have the lithium as the counter ion, and then you have that guy. And so if you use LDA, you can draw that same ionization expression. But now let's compare pKa's. So the pKa of the ketone, the alpha position of the ketone, as we said, was about 20. The pKa of the conjugate acid here is around 35. So now when we compare those, what's the stronger acid? It's the ketone, by a lot. And in fact, this is such a difference in acidity, most people don't even consider it an equilibrium anymore. So for all practical purposes, what you can assume is that if you use LDA on one of these carbonyl compounds, you will get 100% enolization. So that solves significant problems for you. 2 of the 3 problems we saw above were a direct result of having that hydroxide hanging around at equilibrium. It went and attacked your alkyl halide. It would go and deprotonate the monoalkylated product and cause polyalkylation. So that excess hydroxide, the excess base at equilibrium, was the issue for 2 of the 3 of the problems we saw before. If you use a very strong base like LDA, you don't have to worry about those 2 problems. So the only thing you do have to continue to worry about is you still can't use aldehydes. So I'm going to give you kind of a bad, better, best situation. So we've seen the bad, that was the direct alkylation using hydroxide. We've seen the better using LDA, the strong base. The best way of doing this, however, it turns out, is not under basic conditions at all. This is through something we saw a long time ago. I told you it would be back, and here it is. This is through enamine chemistry. So if you take, again, we've seen this before. Take an aldehyde or a ketone. Add a secondary amine. I don't think we need to go through the mechanism of this because we did it way back when, but if you take a carbonyl, an aldehyde, or a ketone and add a secondary amine, we get the enamine. And what you should note is this enamine is very enolate-like. You know, you've got kind of the double bond here and an adjacent heteroatom. It's just in this case, it's a nitrogen, not an oxygen. And so it will behave very much like the enolate, in that if you add a suitable electrophile, electrons come down, get kicked out the alpha position. Let me get that. And under dilute acidic conditions, that hydrolyzes to give back the alpha substituted product. Now the reason why I say this is a superior method is because not only can you use aldehydes here, unlike the previous two, but this is done under very, very mild conditions. Whereas to do the previous method, you needed very, very strong base. Well, there's a lot of things that are sensitive to that strongly basic condition. With enamine chemistry, you're not using base at all. It's just very, very mild acid. And you are doing the exact same transformation. So this is, not only does it allow us to use both aldehydes and ketones here, but it does so under much milder conditions with the enamine chemistry. All right? Any questions on this? Okay, well, so far, what we have been talking about in this chapter have been the, what are considered, let's say, end of alpha substitution. So all that we've talked about up to this point has been just substituting the alpha position, be that with halogens, be that with alkyl groups, just relatively simple alpha substitution reactions. What we're going to spend the rest of this chapter talking about is a second class of reactions, much more useful reactions, that are called condensation reactions. And these condensation reactions, kind of the hallmark of them, is that they will combine two molecules by a carbon-carbon bond with the simultaneous loss of a neutral small molecule. This neutral small molecule is most commonly either water or some alcohol. This is where the reactions, it's these condensation reactions that start kind of looking a lot alike. All right. So the first one that we'll look at, the first of these condensations, is a really famous one. That's known as the aldol reaction. And as I mentioned at the beginning of this lecture, what I'm going to do now is I'm going to start with every new reaction. I'm going to introduce it first by functional group transformation. And it's that way that I would encourage you to learn these. All right. So what the aldol reaction is going to do is it's going to take two aldehydes or ketones, and in the end, it's going to generate either a beta hydroxycarbonyl or an alpha beta unsaturated carbonyl. And the second is by far the more common. All right, so let's see what that actually looks like and how that happens. So I'm going to start with a very, very simple example, probably about the simplest example. And that would be if we start with acetaldehyde. Now, if I take acetaldehyde and I treat it with hydroxide, remember, hydroxide, so we're trying to make the enolate here, but we're using hydroxide as base. So we already saw the pKa difference here. If you're using hydroxide as base, yeah, it can make some enolate, but it's certainly not going to lead to complete enolization. So if you add hydroxide to a regular aldehyde or a ketone, what you're effectively doing in the flask is you're generating some enolate, but leaving some carbonyl. Or said another way, you have some nucleophile and some electrophile. And that's good enough for a reaction. So the part of the solution that enolized will end up going out and attacking the carbonyl, like so. When you think about what that's going to look like, maybe I'll color code this. You would end up with something that looks like that, where the alpha carbon of the enolate goes to form a bond with the carbonyl of a neighbor. And then this is just going to grab a proton from the water, from solvent. And look what that generates. That is your beta hydroxycarbonyl. The reason I call it that is because when we use these Greek letters, we're always referencing the carbonyl. So there's my carbonyl. The carbon right next door is the alpha position. The one beyond that is the beta, and so on down the Greek alphabet. So you can see I have the carbonyl, and in its beta position, I have a hydroxy group. So we call it the beta hydroxycarbon. Now you can isolate these sometimes, but not most of the time. Only when you're dealing with very, very simple, unhindered aldehydes can you isolate a beta hydroxycarbonyl. Under the vast, vast majority of cases, these cannot be isolated because what they do is, I mean, you still got two relatively acidic alpha protons. You're still under basic conditions. So what happens most of the time is the hydroxide base is going to come in and grab another alpha proton. And in this case, those electrons are going to kick in like that and kick out the hydroxide. So usually what you end up isolating from an aldol is that? Which would be the alpha beta unsaturated carbonyl compound. Alright. So we can look at another example, maybe one that's a little bit more complicated. So what if I were to give you this? So in this one, we're still using hydroxide as base. So that will allow for the deprotonation of some of the compounds. So that's what we would end up with in the flask, where you have some enolate and some carbonyl, some nucleophile and some electrophile. And then the nucleophile would attack. And maybe I'll do this, I'll color code it again. Just so. I think the hardest part about doing these is just drawing the products. But you can see what I've done here is it was the alpha carbon of one of the reactants has gone to attack the carbonyl of another one. And once you have them put together like that, it's not so difficult. We just need to protonate the alkoxide. That's your beta hydroxycarbonyl. And then it looks like we still have an alpha proton there. So more than likely, what you would end up isolating is the hydroxide would go and grab that other alpha proton, electrons come in there and get kicked out like so. So the final product of this alcohol would end up being that. By the way, what is so favorable? You know, I keep telling you that, I'll scroll back in just a second, but I keep telling you that the beta hydroxycarbonyl is very difficult to isolate. Why is the alpha beta unsaturated so much more favored relative to the beta hydroxycarbonyl? What's so special about this one? Well, not so much resonance, I mean, kind of, but it's just a highly conjugated system. Right? By doing that elimination of the hydroxide, it gives you a much more highly conjugated system than a beta hydroxycarbonyl was. Same thing's true here, right? You get this nice conjugated system. All right, so I want to show you one more reaction looking at the aldol, because it's going to illustrate 2 points. Number one, it's going to show you what this looks like with a ketone, and number two, it kind of shows you some data as to why we typically do not isolate the beta hydroxy. So one last example of this. What if we were to do the aldol with cyclohexanone? So if you use hydroxide, you're going to end up with some nucleophile and some electrophile. Like that. The nucleophile will then attack the electrophile. In this case, we would get something that looks like that, which would protonate. That leads to the beta hydroxy. And then we do the elimination. Which would give us that. Any questions on any of these examples of the aldol we've looked at? Okay, so I want to just kind of show you some data and illustrate why it is we can't really isolate the beta hydroxy. So if you were to try to do this reaction, if you do this at a cooler temperature, it does allow you to isolate the beta hydroxy. But the yield is very, very low. Or you can heat this reaction up but if you heat it up, it causes the elimination to occur. But it gives you much better yield. So it's kind of, you can get one or the other. You can either have a bad yield of the beta hydroxy, or you can get a good yield of the alpha beta unsaturated. You can't do both under most circumstances. And so for that reason, when people do these aldols, the most common way of doing them is to really do them at fairly high heat, so you get a good yield, but again, that's going to cause the elimination to occur. So the bottom line is the vast majority of these aldols end up giving alpha beta unsaturated carbonyl compounds. All right. Okay, what if you'll note that all three of the reactions that we've looked at up to this point have the same nucleophile attacking the same electrophile. What if we didn't want that? What if we wanted, for instance, a 3-carbon aldehyde being attacked by a 2-carbon aldehyde? By the way, this is what's referred to as a mixed, or sometimes a crossed aldol. Would this work well for us? Could we get a mixed aldol product doing this reaction as I've outlined here? Yeah, right. Because you could make the enolate out of the 2-carbon aldehyde and it would attack the 3-carbon like you want. But the 2-carbon aldehyde could also attack itself. Similarly, you could also make the enolate out of the 3-carbon aldehyde. And it could attack the 2-carbon, or it could attack itself. So if you were just to run this reaction as written, you would end up making 4 different aldol products. Not a good way to run a reaction. So, we have 2 choices. You can either use reactants where only one can enolize. For instance, that one. Only one of those 2 aldehydes can enolize, because benzaldehyde doesn't have any alpha protons. So that could be a successful reaction. Now you might ask yourself, well, if I enolize this, can't it attack itself? So, I mean, wouldn't I be getting 2 different products there? And yes, that's true. And so the way you would run this reaction is kind of important. If you wanted to do this to isolate only one mixed aldol product, the way you would run this is you would have your round bottom flask, and you would put your electrophile and your base. And then you would come in and add the one you want to act as the nucleophile. You would add that dropwise. And that way, whenever you make the enolate, it's a very, very small amount of enolate at any one time, and it is going to be surrounded by a huge excess of the benzaldehyde in this case. So just statistically speaking, you're going to make a lot more of that mixed aldol product than you would of this thing attacking itself. Now the other way of doing this, we still haven't really addressed what if I wanted to make that? What if I did want to use this reactant pair where both of them can enolize? The way we would do that is use a stronger base. Because remember, if you take an aldehyde or a ketone and you give it LDA, LDA can 100% enolize the aldehyde or a ketone. It's a very strong base. It can convert all of that into the enolate. So basically at this point, you would have a flask of nucleophile, nothing else. So once you add the LDA to this acetaldehyde, there's no reaction that's going to be happening because all you have is nucleophile. You don't have any electrophile around, so no reaction is going to happen. Then you would slowly add in your electrophile. And at that point, this reaction can occur in only one way because you have a bunch of nucleophile and then you're adding in a bunch of electrophile.
Does the LDA have to be neutralized before you can do the next step?
No, because you would just use a stoichiometric amount.
So it would just get used up.
Yeah, it would just get consumed. And so doing it in this way would guarantee one mixed alcohol product. All right. Any questions on the mixed aldol? Okay, well, if not, then I think that's probably a good place to stop for the day. So we can go ahead and head into lab, and I'll see you there in about 10 minutes.